Okay, in this last video, we're going to look at another type of addition to a carbonyl compound that is related to carbanions at the alpha position of carbonyl groups, and this is called conjugate or Michael addition. This arises because of the resonance interactions present in the alpha-beta unsaturated carbonyl compound. Okay, so recognize that there's a substantial amount of partial positive charge character there as well as there. We can even write resonance forms that express that. Okay, all right, so this resonance form here is not as good because it has reduced the number of covalent bonds, but when you put a positive charge right here, recognize that it's allylic, and thus we can write another resonance structure that has a full positive charge right there. This is where the most of the partial positive charge character is right here, but there's still a substantial amount delocalized to the beta position. Okay, all right, when a nucleophile approaches an alpha-beta unsaturated carbonyl compound, there are two possible reaction sites right there, and the one that you're probably very familiar with right there. Okay, we call the normal addition to the carbonyl group 1,2 addition, and this is typically the kinetic product. There's more positive charge character at the carbonyl carbon, and thus nucleophiles are more attracted to that position. That's where they're more likely to react. Okay, so in a classic 1,2 addition to an alpha-beta unsaturated carbonyl compound, it looks exactly like all the other carbonyl additions that you've seen before. Okay, you generate the carbonyl addition product, and you add a proton source, and you just get, in this case, the tertiary alcohol that happens to have a double bond in it. Okay, in the Michael addition reaction, the nucleophile adds to the beta carbon to get an enolate anion, and after the proton source is added, you get a compound like this where you have a substituent at the beta substitution. Okay, so the substituent ends up at the beta position. This is called 1,4 addition or Michael addition. Okay, and this is the thermodynamic product. This is the more stable product. Okay, and this is because the enolate anion is actually less basic than the alkoxide anion, and if it goes to completion, this product here, the Michael addition product, is actually the more stable product. Okay, the carbon-oxygen double bond is much stronger than the carbon-carbon double bond, and any reversible reaction is going to favor the Michael addition pathway. Okay, so let's look at a few generalizations that we can make. Grignard additions and organolithium reagents almost always react via 1,2 addition. Okay. All right, so even though we have a double bond in these two substrates here, they're going to do the same reaction you saw several weeks ago that ketones are doing. They're going to just add to the carbonyl group to make the tertiary alcohol. Had this been an aldehyde, it would have made a secondary alcohol. But the only difference here is that the product is carrying an extra double bond relative to the tertiary alcohols that you've seen in the past being made this way. Okay, cuprates and nucleophiles that are derived from carbon acids or any acid with a pK less than 20 or so react via Michael addition. Okay, so the Gilman reagent or the cuprate reagent reacts with this compound, this cyclopentenone derivative here, to produce exclusively the Michael addition product and none of the 1,2 addition product. Okay. Cyanide anion will add predominantly by the Michael addition product, and you get very little of this cyanohydrin shown here on the right. Okay, the amine and sulfur nucleophiles also add predominantly via Michael addition. Okay, so here this thiol reacts with KOH to produce exclusively the Michael addition product that you see here. Okay, and these are reversible reactions. If you look at, in each case, we'll just look at the first one. Okay, so because these reactions are reversible, we ultimately end up making the thermodynamic product, which is the Michael addition product. Okay? All right, so here's a little problem for you. Again, as before, pause the video and do the problems yourself and see if you can predict the products. This third one actually isn't related to conjugate addition. It's just a review problem. And this last one is an unusual conjugate addition product. Okay, so from the first one, we're going to add the ethyl group to the beta position, and the product that we're going to get is the Michael addition product that you see here. We're going to have an ethyl and a methyl there. Okay, this is a Grignard reagent, so it's going to do a 1,2 addition. Okay, so it's going to add here and not do the Michael addition. And the product that we're going to get is that one, the tertiary alcohol. This one is just making an anion and alkylating it. Okay, so we're going to alkylate here, and that should be our product. Okay, we don't get the other product because we're not going to make very much of this enolate here. There's a lot of angle strain when you make a carbon in a 3-membered ring sp2. Okay, so let's look at this last one. How is it we get this cyclopentane ring? Well, we've seen clues as to the origins of this compound in the past when we were looking at malonic ester syntheses of dihalides. Okay, so here we have a halogen already attached in our molecule. This is a cuprate, so it's going to do the Michael addition, and this is going to make this product here. This is a copper enolate. Okay, so the metal is copper, not lithium or sodium or free anion like you've seen before, but you can think of this as being like an enolate. Okay, and once you have that, you can do the classic direct out or intramolecular SN2 reaction, and that gives you the product that you see there. Okay, the last reaction we're going to look at that's related to conjugate addition is a historically very important one called the Robinson Annulation. And in the early days of the development of steroid chemistry, this was a very important reaction for basically adding a 6-membered ring to any ketone that has an acidic alpha hydrogen. Okay, so typically what happens in the Robinson annulation is that we have a simple ketone and an alpha-beta unsaturated ketone like this. We're going to treat it with base at high temperature, and this reaction usually has to go for several days, and we're going to form a new 6-membered ring. Okay, so a 6-membered ring will be added to whatever substrate you had before. Okay, so let's look at this reaction here. Let's look at its mechanism. Okay, there are a lot of things that can happen in the Robinson annulation, and all of the things that you think can happen actually do happen, but there's only one set of reactions that'll move you in a forward direction. Okay, all right. So what happens here is that our base removes this hydrogen here. Why this hydrogen? Why not these hydrogens? Why not these hydrogens? Well, in this particular substrate, this is the thermodynamically most acidic hydrogen because it gives rise to the thermodynamic enolate. This enolate here is a more substituted alkene than the other one. Okay, so right, so that's a tri-substituted double bond. The other one here is a tetra-substituted double bond. So this is more stable. Okay, the enolate is now going to undergo a Michael addition to provide the product here. Okay, and this is an anion here, but this ideally would like to attack this carbonyl, but it doesn't, because that would make a four-membered ring. Okay, so both of these positions here, or both positions alpha to this ketone group, are of comparable acidity. So you can make the anion here without too much of an energy cost. And now, when this attacks, this makes a six-membered ring. And the six-membered ring now basically is making an aldol product, and these last steps could be just described as an example of the intramolecular aldol condensation reaction. Okay, so we make an anion, it does a Michael addition, and then the product undergoes an intramolecular aldol condensation process to produce the product. Okay, let's look at a couple of problems here, and we're going to do a forward synthesis and a retrosynthesis. So in this first one, what is the product of this reaction? Okay, so in this case, there's no question as to what's the thermodynamic enolate. It's the one that's between the two carbonyl groups. That's a much more acidic hydrogen than these hydrogens on the other side of the ketone. Okay, this is going to do the Michael addition. Okay, we'll just write it as the carbanion to make it a little quicker. Okay, always be careful to draw the right number of carbons. That can be a common problem. Okay, so we're going to make the anion on the other side. Now it's going to attack there. And this is going to set up our six-membered ring. We're just going to dehydrate the product like we do other aldol products, and this is the product that we should be obtaining from this reaction. The one shown here, the carbons that you see in blue, came from the starting material on the right. The carbons in red came from the starting material on the left. The red ones came from the starting material on the right. Okay, this last one is a retrosynthesis question, and we're looking at what compounds do we need to put together to make the A ring of this compound. Recognize that this is the bond that we're going to make in the intramolecular aldol step. Okay, so at some point, I don't know what I did there. Sorry, there's some strange doings here. Okay, maybe we, all right, I don't know what happened here, but I think we can, let's see, there we go. Okay, we resized it. All right, so the precursor compound here, or it's not actually a precursor compound, it's only a intermediate in the mechanism. All right, so at some point, we're going to have this compound right here. All right, so we want to make the anion there. And so here are our two ketones, okay? And this is the bond that we're going to make via the Michael addition process, okay? All right, I guess we could think about making this bond here, but this would give us a substrate that's a lot more complicated than making the bond here. This is the simple one, okay? All right, so what are our precursor compounds? We just need the ketone in blue and the alpha beta unsaturated ketone in red. We should be able to treat these two compounds with strong base and have them condensed together to make the Michael addition product that's on the far left here. Okay, so this is all of the videos for the chemistry of alpha carbonyl derived anions and enoids, and I'll stop it here. Okay.